Hi, I'm Chen. I'm happy to present our work on CVPR 2023, Learning Neurovolumetric Representations of Dynamic Humans in Minutes. First, I'll have a 1-minute overview of our paper. The task addressed in this work is accelerating the process of creating neurovolumetric videos of dynamic human performers from sparse monocular videos. The task has applications in AR/VR, video games, and movie production. Although recent methods using differentiable neural rendering have shown promising results, they typically need 10 more hours for training, which is not friendly to novice users. To solve this problem, we propose a novel human representation containing a motion parameterization scheme and a part-based voxelized human representation, which can be trained within 5 minutes to produce realistic volumetric video of a dynamic performer. Here's a comparison of the optimization speed of the proposed method and the baseline. It can be seen that our method has a much faster optimization speed compared to the previous SOTA. Now let's dive deeper into the proposed technical pipeline. A traditional pipeline to learn dynamic neurovolumetric human representations is to first use the deformation field to walk points from the world space to the canonical space, and then regress density and color from the canonical field. Thus, to accelerate the overall convergence speed, we need to accelerate the learning of both fields, the deformation field and the canonical field. The deformation field is typically decomposed into the rigid deformation and the non-rigid deformation. For the rigid deformation, following previous works, we use a linear plane skinny to model the rigid deformation. The non-rigid deformation field is 4-dimensional indexed by XYZ. However, directly modeling it using grid-based representations can result in a significantly large memory consumption. In previous works, neural fields were utilized to represent this field, but training such networks proved to be time-consuming. Directly applying grid-based hybrid representations to model such field will lead to too large memory consumption, which is not feasible as said before. Therefore, it is necessary to compress the field from 4D to 30D. We observe that non-rigid deformation of human geometry typically occurs around the surface instead of in the volume, that is, nearby surface points on a parametric human model to have a similar motion behavior. Thus, we propose a novel motion parameterization technique that models the 3D human deformation in the 2D domain. This enables the modeling of the motion field using 3D voxelized representation to accelerate the training. The design of the model for canonical human fields is also very important to ponder for maximum optimization efficiency. We use the multi-resolution hash encoding to model the canonical human field. We observed that the choice of hyperparameter of the MHE encoding is also very important. For example, when designing the hash table size, if the hash table has a too small table size, the possibility of hash collation increases, thus slowing the convergence. On the contrary, if we set a too large hash table size, the GPU cache miss will increase, thus also hindering fast learning. We observed that different human parts have different complexity. For example, the human face is typically more complex than the limb. Thus, we propose a part-based canonical representation. We split the canonical human model into different parts and build a grid-based representation in each space. For each point, we map it into different parts, query different MHE encoded MLPs, and then aggregate to the final result. Thus, in the final pipeline, for each query point, we first obtain the closest point on the SMPL mesh and get the blend width and UV parameter. We then use the above-mentioned deformation field to warp the point to different part spaces. We then query different parts and aggregate the result to perform neural rendering. Then I'll show you some experiment results to prove the effectiveness of the proposed method. First, let's see some comparison with the baselines. Here's the quantitative comparison between the proposed method and the baselines. Our method has a much faster optimization speed, yet preserves competitive rendering quality. Here we compare our method with NeuralBody. Our method is only optimized for 5 minutes, and the baseline is optimized for 10 more hours. However, our method shows better rendering quality. Here is a comparison with another baseline. Here we show the comparison on a different subject. Our method also has a faster optimization speed and competitive rendering quality. Here is a comparison with another baseline. We show the result of the 360-degree rendering of a static frame in this slide. Here is a comparison with another baseline. Here we show the comparison of the novel view synthesis on a different subject. And we show the result with another baseline. We do evaluation studies on the proposed components and prove their effectiveness. The experiment showed that removing any of the proposed components will lead to the degradation in performance. From the qualitative result, you can better observe the impact of different components of our system. We do ablation on the hyperparameter of the hash table size. This experiment showed the importance of introducing adaptive hyperparameter tuning. We do ablation on the variance of the inputs of the MLP predicting radial deformation. It can be seen that the proposed method had the best effect. We do ablation on the aggregation to show the effectiveness of the proposed aggregation method. We also study the effect of the number of input frames. In summary, we propose a neural framework that achieves 100 times speedup on the training of the neural human representations while maintaining competitive rendering quality. We study a novel part-bit voxelized human representation to distribute the representational power, give a 2D motion parameterization scheme to increase the convergence rate of the human deformation field. For more technical details and results, please check out our technical paper and our website. We are thrilled to be presenting our findings physically in Vancouver at the morning poster session on Wednesday. If you are interested, please don't hesitate to drop by and say hi.